Hi everyone. So this is intended to be a recorded version of my presentation as part of my doctoral defense. At the University of Toronto, doctoral defenses are closed door, and the format are usually a 20 minutes presentation by the candidate, and then followed by the oral examination. And this video is my 20 minutes prepared version of the presentation part of the defense. Um, my PhD supervisor is Professor Pierce Sullivan at the U of T Turbines Research Lab, and I'm also co-supervised by Professor Essel of the Concordia University. My work is primarily in numerical investigation of 3D, especially circular, and also SJA synthetic jet in crossflow. So, starting with a bit of background and motivation, the underlying physics that I'm trying to combat is flow separation, which happens when there's an adverse pressure gradient on a flow surface. This can happen on things like wind turbine or large civil structures. And when it happens on airfoil, it can lead to flow separation, where we usually suffer from increased drag and reduced lift. So one of the ways to get around that is by applying something called active flow control. So in the smoke visualization, with our control, we can see that with red arrows pointing, there's a kind of like a void pocket region. That's the recirculation zone. So the flow is fully separated from the airfoil surface on the upper surface, and that the airfoil is fully stalled. So we're losing a lot of the lift from the airfoil. Now, on the right, with adequate control, what we can do is that we can suppress the separation. The streamline's a lot closer to the flow surface, recovering a lot of the lift back, and the size of the eddies in the wake are also a lot smaller. Now, one of the ways to achieve these active flow controls by using something called synthetic jet actuators, SJAs. They really do come in all sizes and forms and shapes, and this is just an example of what my colleague currently uses in the lab's wind tunnel from microblower, very lightweight, 16 grams, quite a lot of potential to be applied on small to medium UAVs. The way these SJs work, they're kind of similar to your human lungs. There's a diaphragm inside a cavity where alternate between ingestion and expulsion cycle. Now, here's some visualization of how they look in a quiescent environment. You have a laminar jet. It just kind of alternate between ingestion and expulsion cycle and forming these vortex ring that kind of looks like a little donut. Now, if we increase the Reynolds number, eventually it does turn into kind of like a turbulent jet. It still comes out briefly as a vortex ring, but then the flow does transition to turbulent very quickly. Now, the goal of my work was primarily to look at this with more of a 3D aspect of things, especially on circular and also SJs in a cross-flow environment. Now, recall the smoke visualization I showed 2 slides ago in the background where the separations was controlled. That was only taken at the mid-span of the airfoil. So this CAD drawing is actually the same airfoil and showing similar configuration of where the SJ is applied with the blue dotted line mainly in the middle one-third of the section of the airfoil. And the other section uncontrolled are still a part of the physical geometry inside the wind tunnel experiments itself. Now, if we look at a top-down view, and this is zoom into the control region, but then the SJs are not turned on, and we can see that near the trailing edge, the flow becomes or the image becomes more blurry, suggesting the flow is separated and there's a recirculation zone. Now, with control, that same area becomes the streamlines become very smooth, kind of suggesting that the flow was reattached, but that's the effective control zone. The blue section is the SJ area, and if we look at the image on the left, I'll let the CAD drawing, um, we can kind of see that we're only controlling one-third of the section that's after the SJ area. So in the grand scheme of things, the whole wind tunnel, we're controlling maybe 1/10 of the entire airfoil. So there's quite a lot of uh, room for improvement, especially looking at what is causing this bleeding of the unactuated zone to kind of almost like reducing a lot of our would-be active control area. Now, to achieve this, my work is kind of broken into three main phases. Phase one is a more fundamental, looking at a singular, circular, and also SJ in a turbulent boundary layer crossflow. Phase two is split into sort of two sections. First, I look at some of the ways to improve SGA modelings without sacrificing the accuracy, but at the same time, we want to reduce the computational costs if we can. Then I have a baseline 2D cylinder flow. It's called 2D cylinder, but the simulation itself is 3D. Then phase three is where everything comes together, where I'm applying an array of 5 circular nozzle SJs onto the 2D cylinder in hopes to reduce or at least kind of control some of the separation. Now, starting with the work done in year one, that was on phase one, quite fundamental. Have a single circular nozzle SJ in a turbulent boundary layer cross flow. And the main thing I looked at is by changing the strength or the momentum of the SJA. What I saw was that at lower strength, we primarily get something called a hairpin vortex, HV. So the structures isn't able to penetrate very far into the boundary layer. They kind of just stay closer to the flow surface. Now, as we increase the momentum or the strength of the SJA, the jet column get more of a chance to penetrate the boundary layer, at least further in, and forming something called a vortex ring, VR. Now, here on the upper right, I have some time average boundary layer profile, and this kind of shows that all of the actuated case was able to increase near wall momentum, especially for medium to higher momentum jets. And at this area is usually quite hard to measure accurately experimentally with PIV. And we're talking about maybe 0.5 mil to maybe 1 millimeter from the wall, and quite often then the reflection at that area is just gonna be too much that needs to be masked off with BIV. Now, I also looked at the span-wise distribution of the watershed stress. At the midspan, all of the actuated cases was able to increase watershed stress, which are often associated with potential and delaying from separation. And even although if we increase the momentum or the strength of the jet from KC to KC, we have better watershed stress at mid-span, but we're kind of sacrificing it in terms of the span-wise coverage. So we don't always just want to blindly increase the jet momentum. We kind of want to maybe go for a medium blowing ratio so we don't sacrifice too much of the span-wise coverage. Now, moving on to year two, where I looked at how to reduce some of the computational costs of modeling SGA. So the work in year one was done with a whole SGA method. So I simulated cavity, and it's actually a morphing mesh with dynamic mesh. So basically, every time step, the mesh actually moves, and I have to solve, I think, at least 4 to 5 more equations. So I have to solve the new displacement of the mesh in XYZ direction. The displacement has to be diffused inward, and I also have to update the pressure solver, and that's prior to calculating velocity field. But it's a very expensive, costly method. So I looked at what happens if I take away the cavity. I'm applying a velocity boundary condition onto the bottom of the neck, showing the net only case. And finally, I also look at a somewhat common practice of removing the whole SJ only and just applying the boundary condition onto the flow surface directly. Now, the equation I'm using is a analytical boundary condition for laminar pulsing jet called the Wormsey solution. It's a little demo of how it looks 3D on SJA, circular nozzle, in the Y direction is UY. I must say it's a very elegant solution. Um, Prior to applying into CrossFlow, I have did it in a quiescent environment, and also with experimental data. But so on the lower left here, I have some boundary layer uh, profile, time average. And what we can see is that the whole SGA with dynamic mesh and the neck only case with the Webster solution gave near identical time average results. However, if we look at the just law only case where applying a boundary condition directly on the flow surface, there's kind of a bit of an odd spike of near wall momentum where I'm labeling with the red arrow the false momentum. And basically, what happens is that their boundary condition is being applied too close to where their flow is highly unsteady, and we're almost trying to overfit over a constraint model. Uh, and so during the ingestion cycle, some of the flow actually could not exit the computational domain properly and shoots back into the domain. And this false momentum has quite detrimental effect on the near wall washer stress and skin friction coefficient profile, where it ends up increasing the washer stress close to the wall. And again, this is an area that is quite challenging to observe experimentally. Again, we're talking about half to 1 mil, where we might sometimes not have experimental validation at that area. And what it can do is that it can kind of create a false sense of improved performance from the SGA with the numerical work if we apply this connect boundary condition directly on the flow surface. Now, the next thing is I kind of established that we really want to model some part of the neck, but how much do we want to model? And for a parametric study, I'm proposing something that's called a volume ratio. The idea is quite simple. Depending on how much flow we're trying to remove from that boundary condition during the entire ingestion cycle, we want to roughly at least model the same equivalent amount of volume within the neck, but ideally more. And if we're able to satisfy that, the neck only results get very comparable performance results compared to the whole SGA with dynamic mesh, but with significantly reduced cost, which becomes really crucial later on when I try to apply SGAs onto a cylinder or with LES. Now, in year three was when I started my large eddy simulation, but LES are costly and time consuming to debug. And so on the backside, I also extended some of my work of a circular and also SGA and a boundary layer with URANs. And in this case, I'm varying actually three sets of different variables. First of all, I look at the boundary layer to jet diameter ratio, delta 99 to D. And then I looked at the jet momentum or jet strength through adjusting the Reynolds number of the SGA. And then finally, I looked at what happens when I adjust the actuation frequency of, and what I saw was that all these parameters do have quite significant impact onto the SJs in a crossflow environment. And not just on the structures, but it also has an impact close to the wall, especially with the boundary layer height ratio. And the main takeaway that we have was that we don't really want to apply an SGA with too small of a nozzle onto geometry if the boundary layer is too thick. So we roughly want something that the boundary layer is maybe no more than twice as big or tall as the SGA diameter. Otherwise, the actuation might not perform that well. Now, moving on to the LES results. Um, All the LES results I perform are well-resolved LES with the well model. The baseline Reynolds number based on the diameter of the cylinder is 3900. It's in something called the subcritical region where the flow separates as laminar and transitions to turbulent. Validation was primarily done with PIV results. I'm only showing UX here, but Validation also extends to UI, U prime, U prime, V prime, V prime, and U prime, V prime in my thesis. And I also had a very detailed mesh convergence in both the radial spanwise direction, temporal convergence, and also a domain size convergence in the radial and spanwise direction. Quite a mouthful, but quite a few cases that I did on this baseline 2D cylinder. Now, just to make sure I didn't get lucky in the wake, I also looked at comparing validating it with pressure type results um, after done all the mesh convergence. And finally, I also did a little bit of POD on the baseline flow. Quite interesting result. And two main variables I want to highlight. First of all, a drag coefficient of 0.97 and a show hole number of 0.2. Both aligns very well with existing lectures at the similar Reynolds number. Now, moving on to actuated cylinder, I'm applying 5 circuit and also SAAs at a theta equals 90, so it's perpendicular to the free stream direction. Here's a view of the actuator zone. So force calculations are only done on the red region, but the gray zones are still simulated. And I've kind of gone with this approach because we kind of recall the top-down smoke visualization my colleague did in one tunnel. Um, we don't want to just only simulate the red region and put a cyclic periodic boundary condition on the little tiny skinny segment of the cylinder. That's not really what we're trying to solve anymore. We want to see why is the non-actuated zone bleeding into the actuated zone when the actuation is effective. The mesh is a modifiable grid with 10 million cells, maximum Y plus of 1.4, maximum Z plus of 25, resolving at least 89% of the turbulence in the entire domain, and a maximum subgrid scale viscosity to kinematic viscosity ratio is roughly 1. Couple SJ parameters I want to highlight. First of all, the diameter of the cylinder to the diameter of the SJ is 25 to 1. Excuse me. The modulated frequency is 6 Hertz. This comes out to an F plus reduced frequency of 1. This is primarily chosen based on existing literature, not just on a active flow control on a circular cylinder, but also on some of the labs work on airfoil, whereas F plus of 1 and 10 seems to be a effective control, and I've kind of gone with starting with 1. Now, to go with the burst modulation frequency, I'm also applying a duty cycle DC of 50%. And here's how the modulation signal looks like on the lower right. It's actually a blend of two different functions. So there's a step input, but I've kind of tapered it off during the start and the finish of every burst cycle with a sine wave. This is primarily to combat numerical instability, where during the initiation of every burst, it kind of puts a lot of strain on the pressure solver. So this kind of helps the solver just kind of warm up a little bit to avoid any non-realistic behavior, especially close to the boundary condition. Starting result section with a bit of time average streamlines. So now right after baseline case, nothing special, just two primary recirculation zones, symmetric as expected. In actuated flow, even though we have a pretty modest actuated section with just 5 SGAs and the blurring ratio is only 0.84, we're changing the recirculation zone quite a bit. On the upper surface, we're actually almost reducing the length of the primary circulation bubble, and this kind of creates a highly asymmetric profile in the recirculation zone. And if I look at the boundary layer profile, it tells a very similar story, especially if I zoom in. We can see that the actuated case in red dashed line is increasing near wall momentum. This is consistent with what I saw on a turbulent boundary layer in some of my earlier work. But here is actually the lanes, at least suggesting that's the lane separation by at least 45 degrees by increasing the near wall momentum of the actuated case in red. Now this comes up to giving me a lift generation, so increase of lift coefficient from 0 to 0.1, but also came with a mile, or very marginal increase of drag coefficient. Wrapping up with a little bit of coherent structures, here's an isometric view of the computed domain. And if I zoom in and just take a slice of what I show the actuator zone, the red region, and then just kind of filter out or just kind of take out some of the non-actuated stuff. And we can kind of see that the SGA comes out as a burst and array of 4 rows and 5 SGAs, almost kind of discrete. You can almost count them. But then they kind of clump into a larger array pretty soon after. And if we look at it from the side, it tells quite the same story where it comes out, quite discrete, grows a little, but then just form a larger eddy. Kind of goes with the name of the model a little bit. Now, the time average structure kind of looks something like this. Again, I trim off some of the span-wise direction just so it's a little bit more zoomed in. And what we can see is that it's almost like a cumulative effect that we're getting the best performance at the SJ in the middle. And then the first and the last SJ kind of created this barrier. Now, in terms of future work, oh, getting ahead of myself, go. So the original goal of the work is to look at the 3D aspect of a circular and also SJs in crossflow to basically guide future experimental designs. And to achieve this goal, my contributions are as follows. Characterization of the 3D coherent structures of a circular nozzle SJ in a turbine boundary layer, especially with paying close attention to neural structures. Uh, Proposing and also validating a meshing strategy or modeling strategy for circular nozzle SJs, uh, which reduce computational costs significantly. Then leveraging the first two contributions, I extended my investigation into looking at boundary layer height ratio, actuation frequency, and also extending the blowing ratio strength effect. Then finally, apply active flow control with an area of 5 circular nozzle SJs onto a circular cylinder to look at the span-wise effect. In terms of future work, I think span-wise control authority is worthwhile, quite worthwhile. We really do want to know how tightly we need to pack the SJAs and why is the non-actuated zone bleeding into the actuated region so significantly. And then reduced frequency effect, F plus of 10 is also worth looking into. And then power requirement is also quite worthwhile if we want to apply these on, say, like small UAV or battery powered UAV. And integration on a knockoff airfoil would also be worthwhile, especially if we kind of adhere to the theme of looking at the 3D effect, where we only have one segment of the span-wise direction that is or span-wise width that is actuated. And then finally, when the computational cost allows for it, I think we can also do a deep learning reinforcement agent training on a closed loop control scheme. But I think the code would probably have to be somewhere between 100 to maybe 100,000 times faster to achieve that, at least 100 times.